Okay, so today we're going to talk about translations. So in general, we're going to be talking about transformations, and our first one that we're going to talk about is a translation. So first, we need to recall from physics that a vector is a quantity that has both a direction and magnitude or size, and it's represented in the coordinate plane by an arrow drawn from one point to another. So the diagram over here to the right shows a vector. So it's going from P to Q, and you can see the vector there. So the initial point, which is also considered to be the starting point, of the vector is P. So this is right here where it's starting, and it can start anywhere in space. And the terminal point, or the ending point, is Q. So you can see right here is where it ends. So the arrow is going where it ends. So the end of the arrow is the point at which the vector ends. So this vector is named PQ. And again, we're writing that as PQ with an arrow in one direction. This tells us that it's starting at P and ending at Q. So we're reading it as vector PQ. In the past, we've read this as ray PQ, but for our purposes, we're talking about vectors, so we're going to talk about it as a vector. So the horizontal component of vector PQ is 5. And that's because what's happening is we're going in this direction for 5 units. So that's in the horizontal direction. So that's why it's 5. And then, as you can probably tell, the vertical component is 3. And that's because we're going up 3 units. So that's how you can see that the vertical component is 3. So we write this together. We write both the horizontal and vertical component together in what we call the component form. So the component form of this we always are going to write it in the form x comma y, and notice we have these brackets on the end as opposed to parentheses or anything else we've seen. This tells us that it's a vector. So we write it with the horizontal component followed by the vertical. So we're going to write this as 5 comma 3. So this tells me that vector PQ is moved from P to Q. We started here at anywhere in space, and we moved to the right 5 and up 3. So that's what this is telling us. So when we talk about transformations in general, a transformation is a function that moves or changes a figure in some way to produce a new figure, which we call the image. So when we talk about the original figure, we're going to be calling that the pre-image. So that's really important to note, is the difference there between the new figure being called the image and the original figure being called the pre-image. So the points on the pre-image are the inputs for the transformation, and the points on the image are the outputs. So when we talk about transformations, we have 4 of them. We have translations, which we're going to talk a little bit more about today. Then we have reflections, which we'll get to next time. We also have rotations that we'll get to next time. And lastly, we have dilations, which we'll get to the class after that. So all of these are transformations, all 4 of them. So we're going to kind of zoom in first on what a translation is. So a translation is going to move all of our points. It moves all the points of a figure in the same distance in the same direction. So what that means is that this translation is actually going to map or moves the points of P and Q of a plane figure along this vector A, B to the points P prime and Q prime. So every time we do a transformation, we're going to be using primes, which are these apostrophes here. So what this is saying is that P and Q, this is our pre-image, is this segment here. And then when we talk about our image, that's right here. That's when after we've done this translation. So in this case, we're just moving it along this vector, however that vector is being moved. So we can think about it as it's going over in this direction and then up. So that vector would be how all of these things move. And you can see that these would be the same, which is why all of this got moved to over here. So translations will map lines to parallel lines. So as you can see here, PQ is parallel to P prime Q prime. And again, we read this as P prime and Q prime. So let's talk about these examples here. So we're moving the blue figure to the red figure. We know that our blue figure here is our pre-image and red is our image. And we can tell that because the red one has primes and the blue one does not. So what we need to realize is how are all of these points moving? They all need to be moving in the same form in order for this to be a translation. So every point needs to be moved exactly the same. So I notice that all of these points are moving to the right one and they're moving up 2. So if I'm moving right 1 and up 2, I would translate my horizontal component and my vertical component to be 1, 2. Now over here at this one, we actually have a couple things happening. We first need to move it to the red figure, and then we need to move it to green. So we have a couple things. Blue here would be our pre-image, and then red would be our image after our first translation. So that's our first translation. Then we have a second one where our red is our pre-image, and green is our image. So we have two things happening. So to see what's happening first, we know that we're moving it along this vector here. We have A is moving over this many and up, so that's over 1, 2, 3, 4, 5 and up 1. C is doing the same thing, and B is doing the same thing. So to get from blue to red, we're moving it over 5 and up 1. So this vector would be 5, 1. Now to move it down over to get to the green one, we're taking A prime and moving it to A double prime. So it's being moved left 1, 2, 3, 4, 5, and then down 1, 2, 3, 4, 5. And the same thing's happening with C and with B. So we're moving left 5 and down 5. So that would be 5, negative 5 as our vector. Now, if we just look at this in general, is there a way that we could have gone from blue to green immediately? Yeah, we could have just moved it straight down 1, 2, 3, 4 units. So if I was looking at this in terms of blue being my pre-image, and green this time, we're skipping red entirely, is my image, we're moving it down 4, and that's it. So this vector would be 0, negative 4. So this brings up the idea of a rigid motion. So a rigid motion is a transformation that preserves length and angle measure. Another name for a rigid motion is called an isometry. So a rigid motion will map lines to lines, rays to rays, segments to segments. And as you can see here, a translation is a rigid motion. It's preserving everything, all the lengths and all the angle measures. And then to kind of circle back over here to what we talked about with going from blue to red to green is the same thing as just going from blue to green. we have a composition, and you can have a composition of multiple things, but a composition of 2 or more rigid motions is a rigid motion. And what's important about this is that no matter how many rigid motions you perform, the lengths and angle measures will always be preserved in your final image. So over here, as we talked about before, I could go from blue to red and then red to green, or the composition would just be from blue to green. And we can also have compositions of multiple transformations that happen at one time. Perhaps you translate it and then reflect it would be another idea of a composition.